We took an absurdly large neural network, basically a random function with an illegal amount of knobs, put it inside some cursed high-dimensional math space, then kept measuring how wrong its predictions were and nudging it downhill with gradient descent until it somehow learned language, code, mathematics, physics, and the entire emotionally devastating archive of r/IM14, and this is deep. Then we connected it to tools, gave it enough compute to power a small village, and for hard problems we still make it go, let's think step by step, like bro is filling out a 4th grade worksheet with a trillion parameters. And to be fair, it works. Chain of thought, test time, compute, tools, and self-correction are why AI went from autocomplete with a LinkedIn premium subscription to something that can research, write code, and occasionally refactor your entire repository because one button was 8 pixels too far left. But text is kind of a terrible place to do raw thought. Every generated token is a discrete commitment. The model says one thing, then has to continue from that thing, even if its original assumption was already spiritually bankrupt 3 tokens ago. So it goes. First, we should do A because A, we do B. Therefore, delete the database. What the model needs is a way to update its internal understanding before it generates 2,000 words, defending a premise that arrived pre-cooked. That is the idea behind latent reasoning. A normal transformer is basically a one-way conveyor belt. You put X in, it passes through function 1, then function 2, then function 3, and after a lot more neural network sauce, it eventually produces Y. X goes through function 1, function 2, function 3, and eventually produces Y. Each function represents another transformation through the network's layers. Information moves forward through a fixed computational depth, and then the model predicts its output. There is no built-in moment where the model looks back and says, wait, that was deeply unserious, run it again. It can generate textual reflection afterward, but the original forward computation has already happened. A looped transformer changes the structure. Instead of giving every step of depth completely separate parameters, it can reuse the same transformer block or the same group of blocks multiple times. This is read as h at time t plus 1 equals f theta of h at time t and x in normal language. Take the model's current hidden state, combine it with the input, pass it through the learned transformer function again, and get a new hidden state. Each is not a secret English paragraph where the AI is sitting there going, yes, this does appear difficult. It is a high-dimensional tensor, a distributed representation of entities, relationships, uncertainty, possible actions, constraints, and whatever other abstract geometry the model managed to summon through matrix multiplication. Then the state evolved. H0 becomes H1, then H2, and continues refining until HT internally. It is basically the important difference is that the model gets repeated opportunities to transform the same evolving representation before it commits to an output. This creates another axis of scaling. More parameters can make an individual transformation more expressive. More loops can give the network additional computational depth using shared parameters. If the recurrent block contains L layers and runs for T iterations, then its rough effective depth becomes effective depth is approximately L times T. The parameter count does not necessarily increase with every loop because the weights are shared, but the inference compute does. The parameter count stays roughly fixed while computation grows with the number of loops. So no looping is not free intelligence generated from the spiritual power of recursion. Every pass still costs compute, but it lets a model trade additional computation for additional refinement without requiring a completely separate set of parameters at every depth. Humans have a similar mechanism, except ours is usually a looped model is attempting the version where it remains locked in. Many difficult tasks are not simply knowledge problems, they are state update problems. Coding is state, planning is state. Long-running agents trying not to become distracted by their own tool output are extremely state. You cannot solve a difficult software bug by memorizing syntax alone. You must track what the code did, what you changed, what that change affected, which test failed, whether it was already failing, and why the repository now contains a dependency named Fix Everything Final Version 2 Real. State at time t plus 1 equals an update of the previous state using the newest observation. The current state is S at time t. The new observation could be a compiler error, test result, tool response, or something the agent discovered in the repository. The update function integrates that evidence into a new state. Then the process repeats. That is what a competent agent should do. Maintain an evolving model of the task, act on it, observe reality, and correct itself. Not edit the wrong file, misread the terminal, and announce implemented successfully while continuous integration is producing smoke signals. This is no longer just an architectural thought experiment. A current example is Nan Beige 4.23b, a compact agentic model explicitly built around a looped transformer architecture. It has 3 billion non-embedding parameters and 4 billion parameters in total. Instead of increasing capacity only by stacking more unique layers, it reuses transformer layers across depth, and its team-reported benchmark results are slightly absurd for a model this small. On SWE Bench, verified, Nan Beige reports 63.6%, compared with 53.1 for Qwen 3.59b and 44.2 for Gemma 412b. On SWE Bench Pro, it reports 46.9 compared with 33.8 and 21.9. And on GPQA Diamond, Nanbeige reports 87.4%, ahead of 81.7 for Qwen 3.59b and 78.8 for Gemma 412b. So this tiny 3 billion parameter creature is, on several reported evaluations, beating models with roughly 2 to 4 times as many non-embedding parameters. That is a real signal, but do not become spiritually attached to one architecture diagram. Nan Beige is not winning because somebody added a while loop to PyTorch and accidentally discovered intelligence before lunch. Its team also used extensive supervised fine-tuning, real and synthesized agent environments, trajectory-level filtering, test-based validation, and reinforcement learning with both outcome and process rewards. Its evaluations also use thinking mode and task-specific agent scaffold. So these results do not prove that looping alone created the gains. They show something more defensible. Architecture, training, scaffolding, and test-time compute interact. Parameter count by itself is an increasingly bad summary of what a model can do. Capability is approximately architecture times training times, useful computation times verification. Not a literal scientific law, obviously. Please do not submit it to new RIPs and cite vector meridian. This becomes especially relevant with Mythos and Fable. My high conviction hypothesis is that Mythos is likely using some form of recurrent depth computation, iterative latent refinement, or another architecture in the same general family. Maybe it is literally a looped transformer. Maybe it uses a recurrent latent workspace, adaptive computation, mixture of experts routing memory, and some other deeply expensive GPU ceremony. Anthropic has not publicly confirmed the exact architecture, so this is an inference, not a leak, and not a claim that somebody found the weights inside a Google Drive folder named Final Real. But the capability profile is suggestive. Mythos and Fable become increasingly strong as tasks get longer, more complex, and more dependent on maintaining state. They can allocate different amounts of effort, and users describe them as unusually persistent and methodical on difficult coding and research workflows. That is consistent with iterative internal computation. It does not uniquely prove it. Similar behavior could also emerge from greater scale, better reinforcement learning, external memory, agent scaffolding, superior data, or several of these fused into one horrifyingly expensive lasagna. The interesting evidence is not simply that the model scores higher, it is where the gains become largest. GraphWalk tests whether a model can follow graph traversal instructions across extremely long contexts from hundreds of thousands toward 1 million tokens. This is not find the secret sentence hidden in a haystack. The model must maintain and repeatedly update structured state while moving through a graph. Conceptually, it must do this. Graph state at time t+1 equals an update of the current graph state using action t. Take the current graph state, perform the next traversal operation, update the internal map, and repeat without losing the plot. Publicly reported results put Mythos preview at 80% on GraphWalk's BFS, compared with 38.7% for Opus 4.6 and 21.4% for GPT 5.4. That is more than double the Opus result and nearly 4 times the GPT result. One benchmark does not reveal a private architecture, but that particular capability jump is exactly the kind of signal we would expect from a model that is unusually good at preserving and evolving internal state over many computational steps. It does not merely know what a graph is, it can remain inside the graph for more than 7 business seconds. The future reasoning stack probably looks something like this: a latent workspace where the model forms an internal representation of the task, iterative refinement that lets it update that representation, adaptive computation that gives easy problems a few steps and difficult problems more time, memory that preserves state across long tasks, tools that connect the model to external reality, and verification that prevents it from declaring victory because it generated a paragraph with sufficient confidence. A useful system might continue iterating until its internal update becomes small. The distance between the new hidden state and the previous hidden state becomes smaller than epsilon. In plain English, keep refining until the model's internal state has mostly stabilized, or until the compute budget notices what is happening and calls security. Real systems will also need learned stopping rules because more loops are not automatically better. A model can overthink, drift, or repeatedly polish the same wrong answer into increasingly premium nonsense. The goal is not infinite thought. It is useful computation allocated where it changes the result. The future is probably not models generating 40,000 token chains of thought until the context window needs city planning approval. It is models that can reason internally, update their state, check reality with tools, and communicate once they have actually done the work. Less Let's think step by step. Moore found the issue. Here is the patch, the tests pass. This is Vector Meridian, covering the models, architectures, and AI products shaping what comes after the chatbot era. Subscribe before every startup discovers 3 nested while loops and calls it adaptive, recursive, latent, agentic intelligence.